Today, we're going to dive into the story of a single point of light, about 6,500 light-years away. But this is no ordinary star. This is Pulsar B0740-28, and trust me, it's got a wild story to tell. A story of cosmic travel, some seriously bizarre physics, and a heartbeat that's, well, a little unsteady. Let's get into it.
So, when astronomers first got a really good look at the gas cloud around this pulsar, this is what they saw. It looks just like a keyhole, doesn't it? As if something punched a hole right into the fabric of space. But what in the universe could possibly carve out a shape like this on such a massive scale?
Well, it turns out this isn't a static hole at all. It's a wake. You're looking at the trail left behind by something moving unbelievably fast. Think of it like a cosmic speedboat, just plowing through the gas and dust of the galaxy and leaving this incredible glowing trail in its path.
Okay, so first up, let's zoom out and take a look at the wake itself. What can this enormous structure tell us about the journey of that tiny little pulsar at its heart? This whole thing is what we call a pulsar wind nebula. It's basically a giant cloud of glowing gas and energy, and it's all being powered by the engine right at the center, our pulsar, B0740-28. See, the pulsar is constantly blasting out a powerful wind of particles, and when that wind slams into the surrounding gas, it makes it light up. Now, here's where it gets really interesting. We can actually break down this shape into three parts. Up front, you've got the head, which is a perfect bow shock, exactly what you'd expect from something moving at supersonic speed. Behind that, the fan is the tail spreading out. But then you get to the back, and it's closed off. And that is weird. That's not supposed to happen. And this right here is our first big puzzle. A supersonic wake should just stream out behind the object, totally open to space. A closed tail like this just doesn't fit any of the models. So, what is going on here?
The leading theory is pretty wild. We're actually seeing two different chapters of the pulsar's life at the same time. That closed rear end, it's like a ghost of its past. See, for most of its journey, the pulsar was cruising through a very empty, low-density bit of space. Back then, its motion was actually subsonic. But just recently, it plunged into a much denser cloud of gas, and that's when it went supersonic, creating that bright bow shock we see at the front.
The physics at play here is called ram pressure. It's the exact same force you feel when you stick your hand out the window of a moving car. The entire shape of this nebula is this delicate balancing act between the pulsar's own wind pushing out and the interstellar gas pushing back. The closed back is the ghost of its old, gentle, subsonic wind bubble. But the front? That's the violent new reality of it slamming into this dense gas cloud.
Okay, so that explains the wake, but what about the speedboat itself? When we zoom in on the pulsar, well, believe it or not, things get even stranger.
This little dot is our engine. A pulsar is the super-dense, collapsed core of a star that went supernova. We're talking about an object the size of a city that has more mass than our sun, and it's spinning on its axis 6 times every single second. Just incredible. Now, pulsars are like cosmic lighthouses. They shoot out these powerful beams of radio waves from their magnetic poles. And as they spin, we see a pulse of energy every single time that beam sweeps past Earth. There's a pretty solid rule for how this works, a concept called radius to frequency mapping. Basically, for almost every pulsar we've ever studied, the higher the frequency of the radio waves, the closer to the star's surface they're coming from. It's a reliable rule of thumb.
You can probably guess where this is going, right? Our pulsar, B0740-28, is a total rebel. It does not follow the rules. And this is our second big puzzle.
So while a normal pulsar emits its highest frequency radio waves from deep inside its magnetosphere, close to the surface, B0740-28 does the complete opposite. As you can see, for this one, the higher the frequency, the further away from the star the emission comes from. It's totally backwards. And why? To be honest, we're not entirely sure. It completely challenges our basic models of how these lighthouse beams even work.
So we've got a ghost nebula and a backwards radio beam. It can't possibly get any weirder, can it? Oh, you bet it can. Let's zoom in one more time to the most basic thing about a pulsar, its spin. You know, we think of pulsars as the most precise clocks in the entire universe, just gradually slowing down over millions of years with perfect regularity. But this one, its heartbeat, the rate at which its spin is slowing down isn't steady at all. It actually speeds up and slows down its own rate of deceleration, almost like it's breathing.
And these changes happen ridiculously fast. We're talking about noticeable shifts in its spin-down rate on a timescale of just 50 to 100 days. Now, for an object with this much mass and this much momentum, that is just astonishingly quick. It tells us something really dynamic is happening inside its magnetosphere.
So what's causing this unsteady heartbeat? Well, a 2022 study found something absolutely incredible. The changes in the spin-down rate are directly physically connected to the actual shape of the radio pulse we see from Earth. The researchers put it simply: when a pulsar changes, its spin-down rate, changes to the pulse shape also occur. It's like the pulsar has two different modes that it flips between. Most of the time, it's in state 1, it's slowing down faster, and the radio pulse we see is asymmetric. But then, it'll just switch to state 2. Its spin-down slows, and the pulse shape becomes more symmetric, with the back edge getting brighter. A huge global change in its rotation is perfectly mirrored by a tiny change in its lighthouse beam. It's amazing. All right, let's pull all these pieces together. What started out as just a weirdly shaped gas cloud has turned into this deep, multi-layered mystery. This one star is just a perfect storm of astrophysical puzzles. Its nebula is a ghost, telling a story about its past and present. Its radio beam completely defies our standard models, and its very heartbeat is locked in this strange, beautiful dance with the shape of its own radio beam. And that's really why this all matters. Studying a star like B0740-28 isn't just about one weird object. It's about testing the limits of our understanding of plasma physics, of magnetospheric physics, and the fundamental physics of neutron stars themselves. It's a whole cosmic laboratory, all wrapped up in a single star.
And this kind of leaves us with a final thought, right? Pulsar B0740-28 proves that the universe is just full of these incredible objects that break our rules and connect different areas of physics in ways we never expected. It just makes you wonder, what else is out there just waiting for us to take a closer look?